Hello, everyone. This is Paul Coggin from Huntsville, Alabama. I work at New Systems as a cyber subject matter expert. And this presentation, Ignition Under Fire Exploring Cybersecurity Attack Vectors in Rocket Propulsion, is intended to help introduce cybersecurity professionals to the subject of rocket science and how cybersecurity can influence the performance of a rocket, possibly. Now, my interest with rocket science started back when I was a kid watching Looney Tunes here in the U.S., Wile E. Coyote, all, and this gentleman in the upper left there, uh, also a cartoon character, were my initial inspirations for being curious about rockets and how rockets worked. And then later on, as I went to college, I had a math tutor who actually wrote the software to track the Sputnik satellite here in the U.S. And I was very fortunate that Mr. Goldman was a mathematician and a computer scientist, early computer scientist, that wrote that software. That was also happened to help me with my math studies. And up there in the upper right is my math professor, Dr. Randy York, who was very inspirational to me when I was young, working on my undergraduate degree in math, and taught me a great deal about rocket science in the advanced math courses that I took in differential equations, partial differential equations, and other advanced math courses I took with him. And then later on, of course, movies like War Games and the Transformers movie, especially where Soundwave, the Decepticon, uh, goes and attaches himself to the satellite at the beginning of the movie. And then later on, uh, dove in to the effort of earning my fourth master's in space systems, and uh, and so that's how I led up to the interest I have of diving into the subject of rocket science. Now, when you start talking about space systems and cybersecurity, there are four primary segments that we focus on with cybersecurity. There's the space segment, the user segment, the link segment, and the ground segment. And for the purpose of this presentation, we're going to focus on the ground segment. And inside that ground segment is also the rocket pre-launch facilities that we see here in the box on the right. And so like I said, we're going to focus on the rocket uh, and the ground rocket launch portion of the ground segment. Now, when you start thinking about rockets, you think, how many computers could there be on a rocket? Because all you ever see, you see the rocket blasting off, and you see all, the propulsion system executing. But there is actually, besides the propulsion system that you see, uh, with a there's a significant amount of computers on the rocket. Is You can see here in this slide, you have avionics, um, that are helping the rocket with navigation, with star trackers, with IMUs. You might have GPS. You have RF communications back to the ground station, where telemetry data is being sent to report on the status of the rocket, how the rocket is performing, um, and it might be also receiving GPS signal that's also helping the rocket navigate. And then there's going to be the computers that are also controlling the propulsion system. There's going there's going to be propelling control systems. There's going to be control systems controlling the engines, and those are all computers that are controlling different components of the rocket. And from a cybersecurity standpoint, if it's a computer, it's a possible target for cybersecurity influence. It may not be remote access, but it could be, supply chain access or pre-launch access from an insider threat, someone in that supply chain that can influence the performance of computers and control systems on that rocket. Now, I found it interesting as I've done research in recent years on space systems, how many of the new space systems are using Linux operating systems. SpaceX, for example, they use a Linux kernel that they developed uh, for the Dragon and for the Falcon 9 rockets, and so they have their own custom Linux kernel and that they use. So so we're it used to be might be some other predominant real-time operating systems, but what you see more and more of, what I'm seeing in my research, both for satellites and rockets, that Linux is becoming the predominant operating system that many are choosing. Now, one from a cybersecurity standpoint, something that caught my attention looking at attack vectors. How would you go about looking at targeting a rocket? Well, one thing that I came across uh, was the flight termination system, because you see in the news often when a rocket starts malfunctioning that the rocket is disabled, that the rocket will explode and be disabled before it can go fly over a populated area and possibly cause significant damage. And so that jumped out at me as something that would be a strategic target for an adversary, would be the flight termination system. And from what the research I've seen in past history, the flight termination systems weren't always encrypted. More recently, flight termination systems are encrypted, and they have encryption authentication, and so the ground station, if a rocket is starting to not perform as desired, starts to have some kind of failure, the ground station can send a signal to the flight termination system and set off explosives that will disable that rocket so that it doesn't fly over, a populated area, for example. And also, you see quite often with SpaceX where they leverage artificial intelligence, machine learning, a lot of automation. Everything is automated. Uh, Rockets such as theirs are used probably leveraging automated flight safety systems so that the rocket can automatically, without human intervention, uh, detonate a termination system that will destroy the rocket if need be, if it's detected that the rocket is not performing as desired. Now, want to give credit where credit's due with this whole subject that we refer to as rocket science. Um, the Everything is built off of the early work of Isaac Newton. He created the three laws of motion that we will touch on very briefly. Uh, and then later on, there was a gentleman named William Moore, who was a mathematician in the UK, and he published three papers on rocketry back in the early 1800s. Now, and then later on, there was Konstantin Tsiolkovsky, and he was a Russian researcher and scientist, and he came up with what we refer to as the ideal rocket equation. And we will look at the ideal rocket equation briefly, and then we're going to take his ideal rocket equation and look at how we might be able to influence the variables with cyber effects to affect the performance of the rocket. And then after Mr. Tsiolkovsky, there was a gentleman from Germany, Oberth, and Robert Goddard, here in the US, and a gentleman from France, Robert Pelletri. They also came up with similar equations as Tsiolkovsky did for describing how rockets should perform. Now, going back to Newton, uh, what I want to call your attention to is this force equal mass times acceleration. This is going to be important. We're going to see this again with the equation for thrust. So I'll show you that we can interchange with the term force with thrust when it comes to a rocket. And then the mass, when we talk about rocketry, the mass is going to refer to the weight of the rocket, and then acceleration is going to be velocity of the rocket. And this velocity is going to be important to us, so that because we're going to need the rocket to get up to a certain velocity so that it can reach the orbit that we desire. And what we see here, I'll focus on this diagram over here on the right of the rocket, where you see the mass minus delta m, and that m is going to be like your initial weight, the initial mass weight of the rocket when it's fully loaded with fuel, minus the mass of the rocket as it starts burning fuel over a time. As time changes, you're burning more and more fuel, and so the rocket is going to get lighter. It's going to be less mass. And so with the rocket burning fuel, it's creating a thrust, which we're going to refer to here in this slide as force, that's going to be pushing down and pushing that rocket up toward space, and the weight is going to be pushing against, as that thrust is pushing the rocket upward, the weight of the rocket is going to be pushing downward. And this aligns with Newton's 3 laws of motion. And so when the object exerts force on another object, that second object exerts equal and opposite force on the first. So that's what's happening here with the weight pushing down and the thrust, the force pushing the rocket up here. And it's going to be key to remember this velocity here, where we start with we're going to start with no velocity, and as the rocket takes off, the velocity is going to change over time, and it's going to increase its velocity as it goes up and heads towards space. And so, like, we want to get to an orbit, like a low Earth orbit, we're going to need about 7.9, I believe it is 7.9 kilometers per second acceleration velocity we're going to need to get this rocket up in orbit. And so, and that's where we're going to have to focus on this delta V, the velocity that we're going to need to get this rocket to reach our desired orbit. But what we're going to do from a cyber standpoint, we're going to look at how a threat actor might use cybersecurity techniques to try to influence these variables and affect the performance of the rocket. And so, going back to what I mentioned earlier, here is the ideal rocket equation, and what we're showing here is that delta V that I mentioned earlier. So what we have here is the exhaust velocity with the natural log of the mass ratio, and that mass ratio is calculated by the initial mass, the initial weight of that rocket here, divided by the weight of the rocket as it's burning off fuel, which is also equal to the exhaust velocity within the natural log of the mass ratio. Here it is again. This is what MF over ME is this mass ratio here that we have shown here on the slide. And it's also equal to what we refer to as the specific impulse, where specific impulse times gravity, this G sub zero, is refers to as gravity. That's the gravity constant, 8.98, and then we have again the natural log of the mass ratio. In this specific impulse, what that is relates to is the efficiency of the rocket's ability to generate delta V. So also something I want to make you aware of is there's a term called the Holman transfer, and I want to make sure that cybersecurity professionals are aware of this reference to the Holman transfer. And that's basically we're going to get this rocket launched and get it in orbit. That's what we see here, this green circle here. We've got it in its first orbit, and we're going to the Holman transfer, we're going to get this rocket into its in gold elliptical orbit here of 3. So it's going to take 2 specific impulses where basically we're going to fire, once we get it in this orbit 1 here, we're going to apply a specific impulse, basically a thrust, a delta V thrust, where we're going to give the rocket more velocity here, so that it goes into the second orbit, and then we're going to give it a second specific impulse again to give it delta V, so that it will enter into the third orbit. And so that's referred to as a Holman transfer, to get that rocket into the desired orbit. And that was the Holman transfer was created by a civil engineer named Holman from Germany. Now let's get, so we're, as a cybersecurity professional, this is where I was specifically interested in. The reason I wanted to go and study my 4th master's in space systems is I wanted to understand how cybersecurity could apply to the field of space systems, and often referred to as rocket science, and how is that going? How do they converge together? What kind of cyber attacks and could affect space systems, and how do we defend against possible cyber attacks as well? So let's get into some scenarios here. Start talking about some ideas of how we might influence the performance of a rocket. So obviously we've shown in the earlier slides, all of the computers. You got avionics, you've got the engine control systems, you've got the pumps that are pumping, especially, you've got a liquid fuel rocket, where you're mixing the fuels together. You got those pumps, and those have computers that you might influence. You have the different navigation that, with star trackers, the IMU, you got gyroscopes, and you have RF links, you have GPS. You're sending your telemetry data to the ground station over your RF, so an adversary could be trying to jam and spoof you. The spoofing you can make harder because you can use encryption, but the jamming, you'd have to use frequency hopping to prevent somebody from jamming you. Maybe an adversary through the supply chain pre-launch, maybe they could try to target sensors that monitor temperature, pressure, mess with the fuel, and of course you could also have an adversary try to use some kind of directed energy against you as well, to try to influence the performance of the rocket. Let's go back for a moment to the rocket equation that we introduced earlier. And so again, we got the delta V is equal to the exhaust velocity with the natural log of the mass ratio here, where this MI is the initial weight of the rocket divided by the mass of the rocket as we burning off the fuel, which equals the specific impulse, which I mentioned, is this the efficiency that the rocket thrusters are generating, delta V, which is times the gravity constant here, and also again the natural log of the mass rate. So that's what we have going on here. So if we have access to the software, maybe of the rocket through the supply chain or pre-launch, maybe we could influence the algorithms, the variables involved with making delta V calculations, and maybe manipulate the values for the initial mass of the rocket, or we could maybe influence how the mass of the rocket changes after it's launched and affect the performance. Maybe we could manipulate sensors so that the rocket when it's being fueled, that it gets underfueled. It may be, if you're able to mess with the sensors in the supply chain, you could affect how accurate the fuel is of the rocket. Maybe it doesn't get fully loaded with propellant like you needed, and so we could possibly make some changes to the software so that it controls how the fuel is mixed, so that the rocket the combustion doesn't operate as we desire. So, and also you could, like we mentioned, you could spoof the GPS. Maybe you try to mess with the star trackers, mess with the IMU, and to try to get the rocket to not, if you could mess with the navigation, the avionics, if you could influence that during the supply chain or possibly pre-launch, maybe you could make the rocket not perform as well. Maybe try to get it off the intended orbit course, so that it doesn't have enough fuel, that it undershoots or overshoots, where you want it to go in orbit, because you're messing with those settings for the navigation. And as I mentioned earlier, you have your thrust, which is equal to F equal mass, the mass ratio times the exhaust velocity, and what I want to call your attention to is this rocket motor over here. So we have fuel, we have an oxidizer, and we have pumps that are pumping this. So these pumps, they're basically going to have computers, going to have firmware. There's going to be some kind of control system. There's going to be firmware that are controlling these pumps, and that is possibly a target for the supply chain or somewhere in the pre-launch activities, that an adversary might be able to come in and affect the capabilities of the rocket. So that's where it's going to be really important to have physical security all the way through the manufacturing process and the pre-launch, to make sure someone that's not authorized or compromised does not go in and influence to inject defects into these components. And so somebody could possibly be change software, maybe make the sensors spoof messages so that they send messages to the ground that everything is fine, everything is working as intended, but actually the rocket engines are performing not as intended. Maybe it's running hot. Maybe the temperature, you're sending sensor readings at the temperatures where you expect it to be, but it is significantly higher. That there's the pressure inside the nozzle is off. You think that the pressure is at a desired value, and uh, they, but it's totally off, and it's affecting the performance. Maybe you influence the ambient pressure, the pressure of the environment, and you're sending bad telemetry data to the ground, and the rocket is actually making bad calculations because the ambient pressure calculations have been modified and somehow so that they're not performing as intended. Now, here's some theoretical attack trees that I was brainstorming and came up with for some ideas after studying propulsion it, while I was working on the degree in space systems. I started thinking about, well, how would an adversary possibly go and try to manipulate the performance of a rocket propulsion system? And so maybe they could get into the mission control system. Maybe you could alter the fuel flow rates that are being sent to the ground station, and those fuel flow rates are going to affect your delta V calculations. That lower delta V is going to make it where it's like the rocket is not going to reach its intended orbit. And maybe you're not able to put the payload into, say, satellites. You're not going to be able to get your satellite payload put into the orbit that you desired because you don't have enough delta V, enough fuel, because the rocket didn't perform as desired. Maybe you go and compromise onboard control systems, and during the launch, you were able to the thrust is manipulated. The thrust variables are manipulated, so that the rocket is not able to perform and doesn't hit the trajectory that you intended, and so you can't get it into the orbit that you desire. So that'll mess up the mission. Maybe adversary could spoof GPS or try to compromise the aviation, the navigation system, and send in errors so that the rocket doesn't get into the orbit that you intended. Or some maybe possibly an adversary is able to go and modify make modifications regarding the payload. Maybe modify calculations about how much the payload weighs, which or they mess with the timing and sequence of when the payload is supposed to be released, and affecting the performance of the rocket. You, like I mentioned, you could be during the supply chain or during pre-launch, um, possibly influence pressure sensors, which is going to affect your thrust calculations. Maybe manipulate temperature sensors, um, or adversary could maybe use a software-defined radio or other uh, means to jam and spoof communications of the rocket. If weak encryption was being used, it might be possible to crack the encryption and inject commands. But being able to do this real time when a rocket is being launched, you're not going to have a lot of time to be collecting network traffic and cracking encryption and then injecting commands. That's going to be pretty far-fetched to be able to do that, most likely, because you're just not going to have a lot of time to capture traffic and crack it and then test and see what kind of access and capabilities you have. It's not as feasible for a rocket as it may be for targeting a satellite where you have time. Uh, so what is more feasible in my mind is if the rocket was not using strong encryption for the flight termination system. That's where things could get interesting. To influence that flight termination system, it, to be successful, it's either if you're going to send a signal to the flight termination system from an unauthorized ground station, it would have to be using uh, no encryption or weak encryption. Most likely, it would be a scenario that it's not using encryption at all. Maybe it's a legacy, older flight termination system that's being used, so someone can figure out the frequencies and possibly send a command, maybe using an software-defined radio to trigger the flight termination system, uh, or if the adversary is able to remotely, possibly has found some way, maybe there's an insider that's enabled a remote access into mission control, or there's someone physically on site at mission control that's compromised. They may be able to compromise the trust relationship of the mission control network and send a command to the flight termination system and try to get the rocket to detonate. That might be a vector. Um, could be that they go after the engine control unit, the ECU, to try to manipulate the rocket from performing, or again going back into messing with the fuel pumps and say load up bad firmware, uh, manipulate the fuel operations, maybe the algorithms, which is going to disrupt your delta V and thrust calculations and mess up the mission, or go and target, say, the environment sensors for the ambient pressure and manipulate the ambient pressure value, which could negatively affect the thrust calculations and disrupt the mission as well. And it's highly unlikely that someone is going to remotely be able to access the rocket once it's launched. It's going to most likely any attack on the rocket is going to happen during the supply chain, the manufacturing, and the pre-launch activities is most likely when something is going to happen to a rocket. It's very highly likely anything's going to happen remote outside of someone being able to execute a flight termination system command to make the rocket disable itself by exploding. So, so, so everyone right now, zero trust is a real popular conversation in the IT cybersecurity community. So, wanted to throw out some ideas, do some brainstorming about zero trust in rockets, because this conversation is coming. It is going to be a part of the rocket science conversation. There's not a whole lot published on this topic at this time, but I wanted to start throwing some ideas out there. The communications for rocket systems is very deterministic. You got the flight control system, the avionics, the payload, the RF communications network. You got the tracking and telemetry communications that are sending updates to the ground station. You have the RF link for the flight termination system. The flight termination system is typically going to have its own dedicated RF communications. You have the propulsion system. It's going to be getting fed data and making calculations. Though all of that communications between the computers and the control system components. It's going to be very deterministic in nature. Uh, in any kind of access to the rocket is going to use, especially in today's time, more modern rockets, and are going to be using authentication and encryption from the ground station to the rocket, and it's going to have strict control, probably using spread spectrum and with the RF spectrum jumping around, and to secure access. Some of the rockets like that are being operated, the larger rockets today, are using like 3 computers, and they use an actor judge architecture where the 3 computers have to agree before they execute a command. So there's this trust where the 3 computers have to trust each other and agree with each other before they execute commands. So that adds a level of trust. And then the mission control and ground system, that is going to be highly secure. You're Now, one thing is opening things up and making, from a cybersecurity standpoint, real interesting, is the mission control ground systems that are moving to the cloud, using public cloud infrastructure. So that is going to be a whole new can of worms. I don't know of anyone using mission control ground system that's in the cloud for rocket launch operations, but it is certainly being used for satellite communications. For the payload that is going to be on a rocket is moving to the cloud. And then and of course you're going to want, both in the ground station, whether it's a private ground station or in the cloud, you're going to want really strict network segmentation and access control. And that's going if it's a private ground station, you're probably going to be air gapped. If it's a dedicated private ground station, it's going to be air gapped from your enterprise network. But like I said, a lot of the ground stations for satellites for the payload is moving to the cloud. Makes you wonder how long before a lot of the infrastructure for rockets will be moved to the cloud, because everything's moving to the cloud. And something that I found very interesting is that a lot of the newer rockets are using something called time-triggered Ethernet. And time-triggered Ethernet is basically Ethernet that is more deterministic. And with time-triggered Ethernet, since it's Ethernet and it's backward compatible with Ethernet that many of us are familiar with, that leads me to believe that at some point in the future, leveraging time-triggered Ethernet that's providing that deterministic performance capabilities that are required for rocket systems, that we could see software-defined networking and micro-segmentation being used in the time-trigger Ethernet switches, so that you can go and implement micro-segmentation and really granularly lock down the trust relationships between different components on the rocket. So I think I haven't read where that is being designed into a rocket, but I can see in the future, who would have thought that Ethernet would be running on rockets, but now it is with this time-triggered Ethernet. So as things evolve and everything is moving to more software-based architectures, I could absolutely see a time-triggered Ethernet network that's being used for a rocket be managed and controlled by a SDN capability, and also locking down the trust relationships with micro-segmentation. So And so some real world scenarios. One scenario that was documented in the book, The Perfect Weapon. Uh, Apparently, according to this book, The Perfect Weapon, a North Korea missile rocket was disabled by a cyber attack in 2012. So there's one real world example uh, of a rocket that was disabled by cyber. Uh, and there was also Chatham House published an article that an Iranian uh, missile was disabled by a cyber attack. And then Russia had two rockets, 8K, 82K, and the 11S 824F in 1996, and the Zenit 2SB41 rocket in 2011. Those two rockets had unsuccessful missions to Mars. They apparently got up into low Earth orbit. From what I've read, they made it to low Earth orbit. But you remember that Hohmann transfer, where you get the rocket into that circular orbit, that first orbit, and then you want to go and generate delta V to you want to create that specific impulse twice. You want to hit the rocket and give it with more delta V twice, so that it can enter into the desired orbit. Well, in what the Russians are saying, that the rockets were not able to go and complete that Hohmann transfer and go into the orbit trajectory that they desired, because something happened. And the Russians, based from what I've read from the sources online, that they were aware that there was security problems, and some of their scientists or suspect that there might have been some kind of security sabotage to the rockets. Who knows? There's nothing confirming what happened, but they speculate on some of the online sources that some of them are suspicious that something happened to their rocket that could be cyber related. And then there's the HIMARS rocket. Recently, with events over in the Ukraine, nowadays the domains of cybersecurity and electronic warfare are merging together. So I thought I would throw this example up. This is more an example of electronic warfare that the Russians are using against the HIMARS rocket, to jamming it so that it wouldn't perform as desired. So that's four real world examples that are published out on the internet of rockets being influenced by cybersecurity, electronic warfare. Now, if you're interested in space, satellites, rockets, etc., and cybersecurity, I recommend you become familiar with the Aerospace Corp Sparta tool. If you're probably familiar with Modern Attack, well, similar to Modern Attack, the Aerospace Corporation came up with the Sparta tool, and similar to Sparta, the European Space Agency came up with SHIELD. That's another really good tool to be aware of. And another very interesting resource from the Consultative Committee for Space Data Systems is this manual they published on security threats against space missions. That's a very good read if you're interested in security threats to space systems. Really good information in that document. And if you're like myself and you like to read books, I I'm a bookworm. I really like to get books in addition to papers and blogs. And here are the four books that are available right now that are focused on space cybersecurity. This book up here in the upper left corner, this advanced penetration testing, hacking satellite communication book. If you're interested in uh, unencrypted satellite communications, this is a really good book to check out. Um, the satellite network threats, hacking and security analysis. That's another good book. It's one of the original. It's probably the original first book that was published on space cybersecurity. So this is a good book. It's got talks about a lot of historic space cyber attacks that you might find interested in, and then there's the more recent. This is probably the newest, one of the newer books that's out on the market, the Space Security Field Manual, and then Dr. Jacob Oakley. He's got a book, Cybersecurity for Space, that you also should be aware of. So, but that is the presentation, and I have hope you found it interesting. If you're interested in the slides and the references, uh, please reach out to me on LinkedIn, and I will send you a link uh, where you can download the slides if you would like to have a copy of them. I'll share them with you. I appreciate your time reviewing this presentation, and I appreciate any uh, feedback, constructive criticism you may have on it. But hope you learned something from it. Thank you.